All right. So in the previous lecture, we talked about functors, and we looked at the functor laws and how they can be derived from category theory. Now we're going to turn our attention to something which is quite closely related to functors, but builds upon the functor concept and generalizes certain aspects of functors. So a very common pattern that we encounter when we program is that we have some functor f just for the sake of argument with just option, for example. So I have a couple of option values, and then I have a function, and I want to apply that function to the option values. Now, with functors, that works really nicely when we have just one argument. So I have a map which takes an f, which is an a to a b, and then it takes an a and it takes a f a and f b, where f can be a list or an option or whatever. Now, I mentioned briefly that we can define functions like map2, which would be a to b to c, and then it would take an fa and an fb and an fc, and then we can continue and we can do map3 and map4 and so on. But that becomes kind of tedious. And what the applicative functor does is it generalizes this map n pattern for us in a very convenient way, and it does so in a sort of slightly surprising way. So let's have a look at the applicative functor. The way this applicative functor actually will achieve this thing is by taking a function, normal function, operating in sort of the normal world, and then lifting the whole function up into this functor world, whatever it might be, though, for example, an option. Put the whole function in. So when we had our functor laws, we said that, well, okay, the map function, it takes a function, normal function, and turns it from a to b, and turns it into a function from fa to fb. But what the applicable will do is it will take a function from a to b and turn it into a f of a to b, which was exactly the one that we didn't want for the normal functor. And then we can apply this function to some f of a to produce an f of b. And this is a function that we commonly call apply. And why this is what makes this so nice is that, of course, that this b here might be a function. The b might be something from q to z to w to x. And this allows us to partially apply this thing over and over and over again, which is really what we want when we want to generalize map from 1, 2, 3, 4, 5, 6. So that's the basic idea of the applicative functor. So let's have a little look how we can implement this in a concrete way, so that we can look at how we can implement apply for. We start with option. We can look at list later, but we start with option. So let's just define apply for option type. So it will take some function f, which has been wrapped up in an option type. So I'm going to call it f prime, and it will take some x, which is also inside a option type. So these are both options. Now f is option. And in order to be an applicative, you must also have a functor. And to see how this works, I can now say match f prime with sum f. So now I just match on this function here. I know that this must be a functor. That's a requirement. So now I can match on this f, pull out the actual function, which is this guy, and then I can just say map f on x prime. Yes? So this is very similar to what the functor did, but now I don't wrap this up in some any more sum or anything, because this is an option type, this is a normal function, and this is the option map. So this will open up this option, apply the function f, and return. And we're done. And of course then there's the nothing case. So if I didn't give a function, there's nothing to apply. So the only thing we can get out of that is nothing. And this is apply. Hooray! Super simple. So suppose now that I want to use this on some multivariate function. Well, in order to do that, I don't really need to, but it's convenient to define a little helper function, which I'm going to call, to make it an infix function, and I'm just going to define this to be apply. And suppose now I have a function. Let's do a proper example here. So remember, I have this function here, which is the same as apply. And let's do a proper example. So first of all, let me define values c, which I say this is get customer 38. So this will get me a customer, but I'm not sure I will actually get the customer. So this returns an option of a customer, some customer information. And then I can say, well, okay, I'm gonna need let O equal get order status x39z, whatever, some order code that I have, and let m get money and some value. I need 1,000 kroner. Yes, and perhaps I need some other data here from customer 38. And all of these can fail. So the customer might not have any money, the order might be failed, for there's no goods in the warehouse, and the customer might be non-existent. And now I have this function that I have defined, which is called process order. And it takes a customer, it takes an order, and it takes money. So this is what I would like to do. Of course, the problem here is now that these are all options. So I need to somehow, so what of course I could do is I could create a map3, and then I could say map3 process order on these guys. But the other thing now that we have learned about the applicative that we can do is that we can say, okay, I'm going to take process orders, or process order, wrap it in sum. So this actually turns this whole thing into a option of a function of customer to order money. So I wrap this whole function in an option type, and then I can use my newly created apply function. On the customer, on the order, and on the money. And this is pretty. And look how this is. This is almost the same as the line above, where these weren't options. The only little thing is that I have to wrap this thing in an option itself, and then I have this special operator to apply the function to these arguments. Voila. And of course, one of the cool and really beautiful things about this is that sometimes if you have a lot of stuff that can go wrong or something similar, is that you can actually write this like sum f, and then you just create a new line, and then you have some function here like get customer x, and you just call these functions directly. And you get really readable and really beautiful code using this applicative operator. This is very popular in Haskell, not so much popular in F#, this applicative. Now, there's a little trick we can do to even improve on this, just a tiny little bit, to make it even nicer. This act of sort of lifting the function, we talked about this in the previous lecture, we lifted it into this elevated world. So now I just wrap this function in an option. We can abstract that into a function. Someone can create a function which is commonly called pure for various reasons. Pure x would be sum x for the option type. So all this pure thing is, it wraps this thing, and then you would write it like this, pure. That's just a little bit of sort of how things are done in the real world. Now, there's a trick we can do. We can improve on this process order to avoid using pure altogether, and we can actually create a little operator here. I'm going to say let create our own little operator, and that's going to be the option.map function that we had. And now I can actually write this whole thing as process order C O M. Whoa, what's going on here? Okay, so let's have a quick look. What's this thing? So now you see I got rid of the pure, and I changed the first star into this thing, which is the same as option map. So now I take a normal function, apply map. So map just takes a normal function, right? And it takes some value wrapped inside a functor, in this case option. So apply it to an option value. This is, which is the C. And the whole thing now returns, since this is map, returns a option with the partially applied process order. Which just means that now what I have after this step here is that I have something which is sum, and then I have a function which is now not COM but some F, which is an O to an M to a result X. So now I have actually partially applied that. And now actually I have a new function which is already inside an option type, and I can just use the star operator to apply that to the next step and to the next step, and we get the result. Pretty cool. So, applicatives aren't very commonly used in F#, but they are becoming more popular, and the latest incarnation of F# actually has built-in support for them, or sort of built-in. You will see, we can do it ourselves. But when we talk about computation expressions, we will see that the computation expressions now have have support for applicatives. Right, let's do a quick little example, one more example. So we've looked at option, and option is kind of simple. So let's look at something slightly more juicy. Let's take the list functor. How would we define apply for a list? Again, remember, what we have is something which should be apply, should be a list A to B, list A, list B. This would be apply for a list. How would we implement this? Well, let apply. Well, actually we have to do let rec apply, since we're going to have to recurse. Because now we're going to get a list of functions applied to a list of stuff to produce a list of things, right? So we're going to get some f and some x, where f is going to be a list of functions. We could call it fs, functions, and we're going to get some stuff that we want to apply this onto. Okay? Again, match fs with, and the first case we have is that we have a list which just contains a single element, f. So then we just say, okay, we have one function and we're just going to apply that. And again, map f on x, and we're done. The other possibility we have is that we have some f and we have some fxs. And again, we can take this f and map f onto x. And now we need to do something else. Now we have the rest of the functions. And I can't just say, okay, just append this to a new list, because then I'm going to get the list of a list. So what I need to do is I need to use the list append operator, and then I can just say apply fxs on x, and we recurse. And then there's a final case when we pass in the empty list or we do something stupid, whatever, and that's a fail with error. That shouldn't happen. Okay, so what can we do with this thing? We can do pretty fancy stuff. So we can take a function like this. So for example, we could just do, oh my god, yeah. We can do something like +1, +2. So we partially apply add 1 and add 2. So now these are already in lists. And I can create a list from 1 to 2. And what will this produce? Well, first it will take the first function and it will apply it to the first value. So that will become 2. It will take the first function and apply it to the second value. That will become 3. Then it will take the second function, apply it to the first value. So that's +2, that's 3. And then it will apply it to the second value, 4. All right. Well, we could also do something like this. And now we can apply this to 1, 2, 3, and then we can apply that to, since this is now a function of 2 variables, we can apply it to the list 5 to 10. And I'm not going to go through exactly what the result of this will be, but what will happen here is that it will first step here is that it applies 1. That makes a new function which is +1, and then it will apply it to all of these 5 values. So that creates 5 values. Then we go back, then we take +2, then we'll apply it to this one, and then we do. So we're going to actually end up with a list of 15 values. We are doing a double loop here. This is a double loop. So if you would be a C something programmer, you would first have for I, tedious, I++, and then you would have a for J, open up and then do stuff, and then and we can do this with the applicative in one line. That is pretty heavy. And of course, put in a function of 3 variables, and I can do a triple loop. And we can sort of abstract this into this pretty heavy lifting machinery. Of course, for the uninitialized, when you see this thing, it's not entirely obvious what it does, whereas programmers are quite sort of used to reading for loops. But with a little bit of practice, this is fairly natural and very nice way of doing things. So that was basically the applicative and a little bit of the fun stuff one can do with applicative functors. One of their major uses is actually in parsers, where you have context-free parsers. There they absolutely shine, and that's actually going to be an exercise in one of the obliques. All right, that was that for today.